welcome to JEE Practice Series questions. In this session, we are going to discuss solutions of modern physics. So, let's start with this exercise. Problem number 1. An electron and a proton are accelerated through same potential. If their masses are me and mp respectively, then the ratio of their de Broglie wavelength is. So first thing, that whenever a charged particle accelerated through a potential difference V, then energy acquired by that charge is equals to Q into V. And in this case, there are one electron, another is proton. So their charge is same, so they will have same amount of energy. Now, we already know that energy is equals to half mv square. So if we'll multiply by m in numerator and denominator, then we can write mv whole square over 2m. Here mv is momentum of the particle. So we can write expression for particle momentum is equals to root 2m into e. Okay. Now here we need to find out ratio of de Broglie wavelength. So de Broglie wavelength is Planck constant divided by momentum. Okay. So from this equation and equation for momentum, we can write de Broglie wavelength is inversely proportional to 1 over root mass of the particle. So we want to find wavelength for electron and wavelength for proton, and it would be equals to under root mp over me, because it is inversely proportional to root of the mass. So option D is correct in this question. Next question is, if the series limit wavelength of Lyman series is 920 angstrom, then that for the Balmer series. So whenever we talk about the limit wavelength, it means transition takes place from n equals to infinite. Okay. For Lyman series, the lower orbital label n is equals to 1, and for Balmer series, n is equals to 2. And the expression for wavelength is 1 over lambda into r into z square 1 over n1 square, where electron is finally taking place, and minus n2 square from where it is starting. So for limit wavelength n2 is equals to infinite. So for first case we can write 1 over lambda Lyman is equals to rz square into 1 over 1 square, that is 1 minus 0. 1 over infinite is 0. So from here we have got the value of rz square. This is our first equation. Now for Balmer series, 1 over lambda b is equals to rz square, and in this case final transition takes place at level 2. So it is 1 over 2 square minus 1 over infinite square, that is 0. Okay, so we can replace value of rz square, that is 1 over lambda L. So lambda Balmer is equals to 1 over wavelength of Lyman series into 1 by 4. So from here we can conclude that lambda Balmer is equals to 4 times lambda Lyman. So choice B is correct. Next question is, when electron in hydrogen atom jumps from second orbital to first orbit. It means the transition taking place from n equals to 2 to n equals to 1. So first let's write the expression for the wavelength, that is 1 over lambda is equals to r Weber constant into z square 1 upon n1 square, that is 1, minus 1 upon n2 square, that is 2. So 1 upon, so it is rz square into 3 by 4. So from here we can find out value of this constant, that is rz square is equals to 4 over 3 lambda. Okay. Now in next half part it is saying, when the electron jump from third to first orbit, means n2 equals to 3 and n1 equals to 1, then the wavelength of emission is. So 1 over lambda dash can be written as rz square, that can be replaced by 4 over 3 lambda, and final orbital is first one, so 1 over 1 minus 1 over 9. 3 square is 9. So from here we'll get 8 over 9, that can be written as 32 over 27 lambda. So from here we can write lambda dash is equals to 27 over 32 into lambda. So choice C is correct in this case. Next question is, a hydrogen atom is in ground state or excited by a monochromatic radiation of 975 angstrom. Then the number of lines in the resulting spectrum. So it means there is an electron at ground state. It means n equals to 1. It absorbs a photon having energy hc over lambda, and lambda is given here. So this electron transition will go to any higher state. Let's take it as n. So we can calculate this n by using the concept. We can directly apply the concept, or we can use the transition wavelength equation, whatever we want, because we are ultimately trying to find out the absorbed wavelength. So it can be written as 1 over lambda is equals to r for hydrogen, z equals to 1, that is 1 over 1 square, this is first orbital, and let's assume it is going to n square, nth. Okay, lambda is given 975 angstrom, so we can write 1 over 975 into 10 to power minus 10, that is equals to 1.1 into 10 to power 7, that is value of Weber constant, into 1 minus 1 over n square, right? So from here we can calculate and we'll get n square is equals to 16 and n is equals to 4. It means after absorbing this wavelength, electron will rise up to orbital number 4. Now the question is, number of resulting spectrum lines will be. So whenever an absorption takes place or an emission takes place, the transition takes place between two labels. Okay, and finally we are getting the final number of label is 4. So number of spectral line would be the combination of 2, that can be written as MC2. So for this case it is 4C2. Okay, so it is factorial 4 upon factorial 2, and factorial 4 minus 2, that is of course factorial 2. So from here we'll get 4 into 3 divided by, that is equals to 6. It means there will be 6 resulting spectral line. So choice C is correct. Next question is, an accident occurs in a laboratory in which a large amount of radioactive materials having half-life 20 days became embedded in the floor and walls. So the level of radiation is 32 times of the permissible level. Then the laboratory can be safely occupied after. So here we have two information. One is the half-life, it is notation for half-life T/2. It is 20 days. Okay. And initial concentration is 32 times of permissible level. So it will assume that the permissible level is N. Okay. So current status of this radioactive concentration is 32 times of this. Now we can use expression of radioactive decay, okay, and that can be simply written as N equals to N naught into 1 over 2 to power time required for this decay divided by half-life. Okay. So N naught is 32 times of N. So from here we'll get 1 upon 32 is equals to 1 over 2 to power T divided by T half. Okay. So 32 is 2 to power 5. So from here we'll get T over half-life, that is 20 days, and its exponent here you can write that's 1 over 2 to power 5, that is equals to 1 over 32. Okay, so this is equals to 5. So from here we'll get T equals to 100 days. So option D is right. Now let's move to next question. It is saying two radioactive substances X and Y initially contain equal number of nuclei. So let's assume that initially it contains A0 nuclei. X has half-life 1 hour and Y has half-life 2 hours. Then after half 2 hours, the ratio of activity of X and Y. So again we can use same expression, that suppose initial is A0, then after 2 hours amount of X would be equals to A0 into 1 over 2 into T to power T half. Okay, expression is N equals to N0 into 1 by 2 to power T over T. So net time is given 2 hours and half-life X is 1 hour. So this is 2 over 1. So current activity of X is A0 divided by 4. Similarly for Y, having same initial concentration, so it is N0, that is number of nuclei at initial state, 1 over 2. Time is 2 hours and half-life is also 2. So we'll get amount A0 by 4. A0 by 2. So it will take ratio of X over Y. It would be A0 by 4 divided by A0 by 2. So we'll get 1 over 2. So ratio is 1 is to 2. Right. So choice B is correct. Next is, if the binding energy of our nucleon of lithium is 5.60 MeV and helium is 7.06 MeV. And the energy reaction takes place. In this question, this reaction is not written properly. Let me write the correct equation, that is lithium 7 with 1 proton is equals to 2 nucleus of helium. Right. And this question is also incomplete, that the energy acquired by the proton we need to calculate here. Okay. So look, 7 nucleides are in helium, so its energy would be 7 multiplied by energy per nucleon, that is 5.60, and let's assume energy of proton is E, which we want to calculate. It must be balanced by 2 nucleus of helium, and in every nucleus there are 4 nucleides, and energy per nucleide is 7.06. Okay. So from here we can calculate energy acquired by proton, that is 2 into 4, 8, and that is 48, so this is 56.48 minus 39.3. So from here we'll get 17.3 MeV. So correct answer is 13.7 MeV. Next is a percentage of the original quantity of a radioactive material is left after 5 half-life is approximately. Okay, so let's assume that initial quantity is A0, okay, and time is given 5 half-life. So we can write T is equals to 5 T half. Okay. So we can use expression for radioactive decay, that A equals to A0 into 1 over 2 into T over T half. So T is 5 T half and divided by T. Please don't get confused here. Here I am writing T half. It is simply a symbol that represents half-life. It does not mean T by T. It is just notice. So from here we'll get 1 over 2 to power 5, that is A0 by 32. So the question is asking that how much percent is left. So if we want to calculate the percent, then it is left amount divided by initial amount and total multiplied by 100. So from here we'll get 100 by 32%. That is approximately 3%. So choice B is correct. Now next is Ka X-ray emission line of tungsten occurs at lambda equals to 0.021 nanometer. Then the energy difference between K and L levels of atom. So it is very direct relation that energy difference between two levels is equals to H into C over lambda, where H is Planck's constant, C is speed of light, and lambda is wave. So we can just put their respective values. Either if you want to put value of Planck constant in terms of electron volt, or let me elaborate the complete procedure, that you can put this Planck constant, that is 6.64 into 10 to power minus 34 in joules. Okay, the speed of light is 3 into 10 to power 8, and lambda is given as 0.21. So it is 0.21 into 10 to power minus 9. And we'll get this energy in joules because we are taking Planck constant in terms of joule. Okay. So if you want to convert joules into electron, then divided by charge of an electron, that is 1.6 into 10 to power minus 9. Okay, so after solving this, it will solve this expression. Then we'll get 0.59 into 10 to power 8. That is 59 into 10 to power 6 electron. That is equals to 59 mega electron. So choice C is correct in this question. Let's move to next question. It is saying a photoelectron work function of metal is 1 electron. So work function is given. Phi equals to 1 electron. And light of wavelength is falling on that surface. That lambda is equals to 3000 angstrom. So you can write 3000 into 10 to the power 10 meters. So the photoelectron will come out with approximate speed. So first of all, we need to calculate energy acquired by emitted electron. So this energy is equals to hc over lambda, that is energy of incoming photon, minus work function of the metal. So because we want to calculate speed in meter per second, so we need to put every value in terms of joules. So Planck constant is 6.64 into 10 to the power 34 into 3 into 10 to the power 8, that is speed of light, divided by the given wavelength, that is 3000 into 10 to the power 10, it was an angstrom, and minus work function. Work function is given in electron volt, so we need to convert this value in joule. And in joule this value is 1.6 into 10 to the power minus 19 joules. So now from here we can calculate the energy. So this, and now this energy can be equated, whatever energy amount we are getting, it can be equated by 1/2 mv square, where m is mass of an electron, that is 9.1 into 10 to the power minus 31 into v square, and this is equals to energy we have calculated from this. So from here we'll get the speed, that is 2e over 9.1 into 10 to the power minus 30. So we substitute amount of energy from first equation, and from there we'll get 10 to the power 6 meter per second. So right answer is 10 to the power 6 meter. Now next is a surface irradiated with the light of wavelength 480 nanometer that gives out electron with maximum velocity v, and the cutoff wavelength is 600 nanometers, right? And the same surface will release electron with the maximum velocity 2v meter per second if irradiated by the light of wavelength. So look here, cutoff wavelength is given lambda naught, that is 600 nanometers. Okay. In first case wavelength is given lambda 1, that is 480 50 nanometer, and for that speed of electron is v. Okay. In second case, lambda 2 is not given, which we need to calculate. Because metal is same, so this lambda naught would remain same, and the velocity of emitted electron is 2v square. So if we write expression for energy acquired by an electron emitting from the surface is equals to hc over lambda, so we can take it as common, hc over lambda 1 minus work function, that is hc over lambda. So this is the general expression. So we can write expression for both the cases. So for first case it is hc 1 over lambda 1 minus 1 over lambda naught is equals to half mv square, because in first case speed of emitted photoelectron is mv square. In second case, this is hc 1 over lambda 2 minus 1 over lambda naught is equals to half into n into 2v square. Now we will divide these two equations, equation 1 and equation 2. So from here we will get 1 over lambda 1 minus 1 over lambda naught is equals to 1 over lambda 2 minus 1 over lambda naught, that is equals to 1 by 4, because the rest of the part get cancelled. Okay, so from here we'll get 4 upon lambda 1 minus 4 upon lambda naught, and we can take it on other side, or you can write plus 3 upon lambda naught, and just doing mathematical manipulation, that is equals to 1 lambda. Okay, so lambda 1 is known, that is 480. So this is 4 divided by 480 plus 3 divided by 600 is equals to 1 upon lambda. Okay, so if we'll just solve this expression, so let's do some mathematical exercise. Write it here, that 1 over lambda 2 is equals to, we can further simplify this as 1 divided by 120 and 3 divided by 200. Okay, so if we'll take LCM of this, then this is 20 into 6, this is 20 into 10. So from here we'll get 20 into 60. And for first element we will do, then we'll get 10 plus for second term it is 6, if I'm not wrong. So it means lambda 2 is equals to 20 into 60 and divided by, let me check my calculation, it is 1200, and if we divide the first is 10, yeah, it is right, upon 60. So we can further eliminate this term, that 5 and there is 4, this is 15. I think I have committed some mistake, so let's check it again. From here we'll got 1 upon lambda 1 minus 1 upon lambda naught, and 1 upon lambda 2 minus 1 upon lambda naught, that is equals to 1 by 4. So from here we'll get, okay, this is minus 3 upon lambda. It should be minus 3. So this is 10 minus 6. Here I have got it. So this is 10 upon 6, so it is divided by 4. Only 4 would be there. So from here we'll get lambda 2 is equals to 300. Yeah, it is right. So this is 300 nanometer for second case, but in this question no option is given, so we can opt for this 300 nanometer or any closer wavelength. Now let's see next question. It is saying a monochromatic source of light is at distance d. So a source is here and this is a surface. The distance is d, right? And photoelectrons are ejected at the rate n electrons per second and energy of electron is E. Now source is brought near. Next case, source is brought at distance d by 2. So what would be the effect? So in this case, we have to be very much clear that whenever photoelectric emission takes place, the energy of electron depends on frequency of the emitted photon or photon falling on the surface. So as the source remains same, it means there would be no change in the energy of emitted electron. So energy would remain same. Second is n, rate of emission. Rate of emission is always proportional to intensity of light. Okay. And intensity can be defined as power per unit area. So it will take circular surface, omnidirectional. So it is 4 pi d square in first case. Now when we brought it near, then it would be I dash is equals to P over 4 pi d by 2 whole square. Right. It means new intensity when we brought source near would be 4 times of the initial intensity. And number of emitted electron is proportional to the intensity. So new rate for electron emission would be 4 times to the previous one. So emission rate would be 4n and energy would remain same, that is E, means option C is correct. Let's see next question. A radiation of 2 photon energies twice and 5 times of work function. So in first case there are 2 photon energies are given. Let's take E1. E1 is twice of the work function. So if we'll take work function 5, so it is 2 5. And in second case it is 5 times of the work function, 5 5. Now these two are incident successively on a metal surface. The ratio of maximum velocity of the photoelectron emitted in 2 cases. Right. So let's write the equation. Energy of an emitted electron is equals to energy of incoming photon minus the work function. So for first case, energy would be 1 over 2 m into V1 square is equals to 2 5 minus 5. Because first case it is 2 5. So from here it will get it equals to 5. For second case, half mv2 square, the incident photon energy is 5 into work function minus the work function. So its energy is 4. So we will take the ratio of these two equations. then V1 over V2 whole square is equals to 1 over 4. So from here V1 over V2 can be calculated, that is equals to 1. So right choice is option number A. Now let's move to next question, question number 14. When a monochromatic point source light at distance 2 meters from the photoelectric cell, then the cutoff voltage and the saturation current respectively 0.6 volt and 0.18 milliampere if the same is placed at distance 0.6 meter away. Okay. Then what is the nature of photoelectric cell? So please keep in mind that energy of emitted electron is depend on frequency, okay, and the stopping potential, that is E into V naught, is also dependent on frequency. Okay. So if the light source would remain same, then there will be no change in cutoff voltage, right? It means the stopping potential will remain 0.6. So choice B is right here. Still we need to check the current. The amount of saturation current depends on number of emitted photoelectrons, which is proportional to intensity, right? As you know that current is net charge, that is N into E over T. So it is proportional to number of emitted electron and N is proportional to intensity. So here we need to check that change in intensity. So first case, intensity is power divided by 4 pi d square, that is 4 pi into 0.2 whole square. And in second case, I2 is equals to P over 4 pi into 0.6 whole square, right? It means if we take the ratio, then I2 is equals to I1 by 4. So intensity is reducing by the factor 4. It means net current will also reduce saturation current by same factor. No, this is 2 by 6. So we'll get from here 36. So it is reducing by factor 9. 36 divided by 4, because the square of 6 is 36 and the square of 4 is 4. So it means your net saturation current is reducing by factor 9. Initial current was 18 milliampere. In new case, it is 18 milliampere divided by 9. So the saturation current will be 2 milliampere. So in this question, option B and A are correct. B and D are correct. Next is, the electron in hydrogen atom makes transition from an excited state to ground state. Which of the following statements are true? Okay. So first let's talk about energy of an electron which is taking transition from one orbital to another. So energy of electron in any orbital for hydrogen atom is 13 in magnitude, it is 13.6 over n square electron. Okay. And when electron is jumping from higher state to lower state, it means it will lose certain amount of energy. Okay. And the relation is total energy in magnitude is equals to magnitude of the kinetic energy, okay, and potential energy is always twice in magnitude of total energy. Here is very important point you must keep in mind, that whenever any particle or any object rotates about a fixed point, be it nucleus or some object in mass, if we'll talk about gravitation, concept of gravity, then we'll get this kind of relationship between the energies. This relation is also valid for satellite revolving around Earth. Anyway, now let's see options. It is saying its kinetic energy increases and its potential energy and total energy decreases. Next is its kinetic energy decreases, potential energy increases, and total energy remains same. Next is its kinetic energy, total energy decrease, and potential energy increase. And next option is its potential energy, kinetic energy, and total energy decrease. So in this question, option D must be right, that when electron jumps from higher energy to lower energy state, its all form of energy must decrease. Next is, let U denote one atomic mass unit. One atom of the element of mass number A has mass exactly equals to A into U. So what is value of A? So here we need to recall the definition of one atomic mass unit. One atomic mass unit is defined as 1/12 of the mass of carbon 12. Okay, so here if mass number is A equals to 12, then the atomic mass of that particular atom be exactly equals to A into atomic mass unit. So it is valid only for A equals to 12. Let's see next question. Two nucleons are separated by one Fermi. The net force between them, if F1, if both are neutrons, F2 if both are proton, and F3 if one is proton, another is neutron. So look, nuclear forces are different from electrostatic forces, because in that case, charge of the particle does not matter, and these act like binding forces. Okay. So when both the particles are neutron, so there will be no effect of charge. Okay, so it means there is nuclear force F1. If one is neutron, another is proton, which is given in case number 3. Again, there is no involvement of charge because one is neutral. So force F3 is also equals to a binding nuclear force. So we can say that F1 is equals to F. Both are binding nuclear force. But force F2 is acting between two protons. Okay. And both are charged particles. There will be repulsive electrostatic force, and in magnitude, electrostatic force are smaller as compared to nuclear forces. So this force must be smaller. F1, F3. So choice C is correct. Next is, a sample of radioactive material has mass m. Its decay constant is lambda. Molecular weight is m. Avogadro number is Na. So initial activity of the sample. So initial activity of the sample A0 is always written as rate of decay or decay constant multiplied by initial number of nucleons. Okay, or initial number of atoms. So this is lambda. First we need to calculate number of moles. So number of mole is mass of the material divided by its molecular mass, and the number of atom can be estimated by multiplying Avogadro number. So initial activity is lambda m Na over m. So choice C is right. Next is, the activity of a sample of radioactive material A1 at time t1 and A2 at time t2. It means its mean life is t. So in this question, the activity of a sample at two time instant are given and its mean life is given. So we have to identify the interrelationship. So we'll go by the radioactive decay expression, that is A equals to A naught e to power minus lambda t, where lambda is decay constant. So for first instant t1, A1 is equals to A naught e to power minus lambda t. For second instant, A2 is equals to A naught e to power minus lambda t2. So from here we can check A1 over A2. So A1 over A2 is equals to e to power minus, we can take common, or we can write t2 minus t into lambda. Okay. Now decay constant is given, so decay constant is 1 over mean life, so it is E into t2 minus t over t. So from here we can write A2 is equals to, we will just shift this exponent, then it is A1 into, now it is going into denominator, so we can write it as t1 minus t2 over t. Okay. So option C is correct, although there is a printing mistake. There should be an exponent center. So A2 equals to A1 into t1 minus t2 upon t. Now next is, a radioactive nuclei X decays simultaneously by two different processes which have a decay constant lambda 1 and lambda 2. Then the effective decay constant of the nuclei. It means X is decaying with rate lambda 1 in Y, and simultaneously X is decaying with lambda 2 constant to Z. Now we have to find out effective decay rate. So we can correlate this problem by a simple analogy, that suppose there is a water tank and there are two different holes. From one hole, water is coming out with 15 liter per second, 5 liter per second. And for second, let's take it is coming out with 10 liter per second. So what is the outflow of water for this tank? There will be sum of these two. So net outflow rate is 15 liter per second. Similarly, one part is decaying by lambda 1, another is decaying by lambda 2. So effective decay should be equals to lambda 1 plus lambda 2. So option A is correct. Let's move to next question. An orbital electron in ground state of hydrogen has angular momentum L1, and an orbital electron in the first orbit in the ground state of the lithium has angular momentum L2. So if we'll go by Bohr's atomic model, then angular momentum of an electron, that is equals to mvr, must be equals to n h over 2 pi. Here h over 2 pi is constant, that is Planck constant divided by 2 pi, and n is the number of orbitals in which electron is orbiting. So for hydrogen and for lithium, both electrons are in the ground state. It means value of n is same. It means they will have same angular momentum. So option A is correct. Next question. Question number 22. The minimum wavelength of X-ray that can be produced in college tube depends. Okay, so look, wavelength is always dependent on energy. Okay, because the generated wavelength is corresponding to energy Hc over lambda. This is the radius. And energy of the charged particle is depending on the potential difference across the tube, that is V, and charge of the particle. Okay. So this energy is equals to Q into. So from here we can say that the minimum wavelength of X-ray can be produced is always proportional to maximum energy. Okay. And that is proportional to potential difference between cathode and anode. So choice D is correct in this question. Next is the potential difference. This is based on previous problem, that the potential difference V is 20,000 applied across X-ray tube, then the cutoff wavelength. So this is the potential difference. So energy acquired by electron is equals to Q into V, that is charge of an electron, into potential difference, and it can be compared with Hc over lambda. So from here lambda can be calculated as Hc divided by E into V. So H is 6.6 into 10 to the power minus 34 Planck's constant into 3 into 10 to the power 8 divided by charge of an electron, that is 1.6 into 10 to the power minus 19 into potential difference applied across this tube, that is 2 into 10 to the power 4, 20,000. So from here we'll get 6.21 into 10 to the power minus 11. So choice B is correct. Next question is, if the potential difference applied across collized tube is increased, then which option is correct? First is, the wavelength of Ka line will increase. Second, the wavelength of Kb line will increase. The difference in wavelength between Ka and Kb line will decrease, or none of these. So look, K and Kb lines wavelengths are defined on the basis of transition is taking place, right? That if transition is taking place from orbital 2 to 1, okay, then it is, if electron transition is taking place from 1, then it falls under Ka line. So these Kb and Ka lines are depending on the transition number. It does not depend on the potential applied. So there will be no change in the wavelength, okay, of Ka line and Kb line. And if there is no change, then there will be no change in difference between them. So this is also not correct. So none of these options is correct, because there would be no effect on the wavelength of K line or Kb line due to change in potential difference across collized tube. Now next is question number 25. The maximum energy of the photoelectron emitted from the surface depends on intensity of the radiation, potential of the collector electrode, frequency of incident radiation, or angle of incident radiation. So if we'll write the expression for photoelectric emission, that is energy of incident photon, that is h into nu, minus the work function of the surface. And this energy can be plotted with respect to frequency like this after this subtraction. So basically, energy of an emitted electron depends on the frequency of incident radiation. Now let's see next question, that when a nucleus with atomic number Z and atomic mass A or mass number A undergoes to radioactive decay process. So this is Z, X, A. It is going through a radioactive decay process. So first is both Z and A will decrease if the process is alpha decay. Okay. So in case of alpha decay, there is 2 reduction in atomic number and 4 in mass number. So option A is correct. Second, Z will decrease but A will not change if process is beta plus decay. So in case of beta plus decay, there is reduction in atomic number, but there is no effect in mass number when beta plus decay takes place. It means this is also correct. Third one, Z will increase but A will not change. So when beta minus decay takes place, then there is increase in atomic number, but mass number remains constant when beta minus decay takes place. So it is also right. Third, Z and A will remain unchanged if process is gamma decay. So whenever gamma decay takes place, there is no change in atomic number or mass number. Okay, so it means this is also correct. So in this question, all 4 options are correct. Next is when the nucleus of an electrically neutral atom goes through a radioactive decay, it will remain neutral after the decay of process. So look, whenever alpha or beta minus decay would take place, there will be reduction in number of protons. Okay, or in one case there is increase in number of protons. So it will create the electrical imbalance. Okay, but if gamma decay is taking place, there is no difference in mass number and atomic number, and there is no difference in mass number. It means it will remain electrically neutral. There is another very interesting process, that is electron capture. So whenever in a nucleus electron capture process takes place, then electron and proton get combined and it get converted in form of a neutron inside the nucleus. So although electron capture is taking place, but it is already compensating a proton, okay, and increasing the neutron, so it will remain balanced and electrical neutrality will maintain. Okay. So choice C and D both are correct in this question. Now next is, which of the following assertions are correct? A neutron can decay to a proton only inside the nucleus. It is not correct. Because here is the condition is given only inside the nucleus, which is not right. Next is, a proton can change to neutron only inside the nucleus. It is right. When electron capture takes place inside the nucleus, then proton get converted in form of nucleus. Okay, but this process does not take place outside of the nucleus. So why option B is correct. Next is, an isolated neutron can change into proton. It is right. That's why option A is considered wrong, because here it was given that only inside the nucleus. Next, an isolated proton can change into neutron. It is not right. This process takes place inside the nucleus only during electron capture process. Okay. So option B and C are correct in this question. Next, two identical nucleus A and B have same radioactive element undergo beta decay. So A emits beta minus particle and changes to A dash. So if A having atomic number Z and let's take mass number Y. So when it gets reduced to beta minus decay taking place basically, so it get converted in form of A dash. And B emits beta minus particle, so for B we can write ZBY. And when beta minus decay take place, then there will be increase in atomic number and mass number would remain same when beta minus is taking place. And it is further going through a gamma decay. So in case of gamma decay, there will be no change in this. Because gamma is 0 gamma 0. There is no change in mass number or atomic number. Okay, then we need to answer these questions. A and B have same atomic number and mass number. So here we can see that A and B dash both having same atomic number and same mass number. So choice A is correct in this case. Okay, let's read rest of the options if some are correct. That A dash and B dash have same atomic number but different mass number. It is not correct. A and B dash have different atomic number but same mass number. It is not correct. And next is A dash and B dash are isotopes. This point creates confusion. Okay, because there is same atomic number, but unfortunately there is same mass number also. So we can't keep these elements in category of isotopes. So only option A will be correct. Okay, next, a nuclide A undergoes a decay to another nuclide B, and that undergoes beta minus decay. So, okay, this is not A decay. Let me make it correct. It is alpha decay. So, question is, a nuclide A undergoes alpha decay and another nuclide B undergoes beta decay. So which of the following options are correct? So please keep in mind that alpha nucleus are heavier as compared to beta particles or gamma particles, and they are slow in speed as compared to beta particles. Okay. So whenever alpha particle emission takes place, they move slowly and they are all having almost same speed. Okay, so option A is correct. Next, alpha particle emitted A may have widely different speed. It is not correct. Beta minus particle emitted B will have almost same speed. This is not right because beta is relatively lighter particle, so they widely get scattered and they having different speed. Okay, so option A and D are right in question 30. Next is, in an electron transition inside the hydrogen atom, the orbital angular momentum may change by. So look, suppose we are taking an assumption that an electron is initially at orbital number m plus p. Okay. Now it is jumping down to another orbital that is n equals to m. So we can write the change in angular momentum delta. that is L2 minus L. Now according to Bohr's model, it is n into h over 2 pi, the angular momentum. So we can write m plus p into h over 2 minus m into h over 2. So change in angular momentum is equals to p into h over 2, where p can be any integer. It can be 1, it can be 2, it can be 3, or so on. So if we'll put p equals to 1, then we'll get h over 2 pi. If we'll take p equals to 2, then we'll get h over pi. And these two options are not possible. So option B and C are right. Next is an electron with kinetic energy E electron volt collides with hydrogen atom in the ground state. The collision will be elastic if the following conditions are true. So first we need to check that suppose there is an electron in ground state. Okay. And if any collision takes place, so whenever this electron will absorb the incoming photon or incoming electron, here it must be written as photon. So it must jump to the nearest level for minimum energy, that is n equals to 2. So let's calculate that what is the minimum energy required for absorption of an electron or a photon coming towards this ground level. So look, if you calculate energy, that is 13.6 over n square, right? So that energy difference between these two levels would be 13.6 into 1 over 1 square minus 1 over 2 square. That is 4. So this energy difference would be 13.6 into 3 by 4. So the minimum energy difference for absorption is equals to 10.2 electron. Now the question is why we are doing this exercise. So look carefully. Here we need to judge a condition for elastic collision. So elastic collision suggests that energy before collision must be equals to energy after collision. Okay, this is just condition for elastic collision. So if absorption process would take place, then the energy will not remain conserved, right? If this energy is sufficient, incoming energy is sufficient, so that electron can absorb it and it transition to level 2, then there will be change in energy. Okay. And for after that, the collision will not remain an elastic collision. So for elastic collision, we need to avoid absorption of incoming electron. Hence, this electron energy or photon energy must be less than this energy difference. So condition for elastic collision would be E less than 10.2 electron. Now question number 33. An electron is in excited state in hydrogen-like atom. It has total energy minus 3.4 electron volt, and the kinetic energy of electron E and de Broglie wavelength is lambda. So we need to measure this de Broglie wavelength and kinetic energy. So look, the total energy of an electron is always equals to kinetic energy in magnitude. Okay. So if total energy is minus 3.4 electron volt, it means the kinetic energy is equals to 3.4 electron. Means E is equals to 3.4. One thing is sure. So these two are in our favor. Next is the de Broglie wavelength. So if kinetic energy is known for electron, then its momentum can be calculated. Momentum is root m into E. So we can put here that is root 2. Mass of electron is 9.1 into 10 to power minus 31. And don't forget to convert this energy into joules, because we want a speed in wavelength in meters. So this is 3.4 into 1.6 into 10 to power minus 90. All these values are under. And de Broglie wavelength is h over p, where h is Planck's constant, that is 6.64 basically into 10 to the power minus 34, and substitute value of momentum from here. Okay, so after calculating this, we'll get the wavelength 6.6 into 10 to the power minus 10 meters. So choice B is correct. Now next question is, let the potential energy of a hydrogen atom at ground state be zero, then the energy of first excited state is. So first we need to check the energy at total energy at ground state. So the expression for energy is 13.6 over n square for total energy. Now the ground state n is equals to 1, so it is 13.6 electron. This is total energy at ground state. So according to this condition, the potential energy at ground state must be twice of this. That is twice of 13.6, that is 27.2 electron. Okay, but this gap is equals to 0. In this case it is saying if the potential energy at ground state is equals to 0, it means there is addition of 27.2 electron volt at each level. Right, that's why we are getting 0 electron volt at ground state. So then energy in the first excited state will be, so it will take energy in the first excited state. So E is equals to 13.6 over n square, that is 2 square. So from here we'll get energy is minus 13.4 electron. It was for general condition when the energy follows this equation. Okay. But in this question it is saying that you need to consider potential energy equals to 0. So it means you need to scale up by 27.2 electron. So if we modify the available energy at second level according to this scaling formula, that at each level you need to add this amount, then we'll get 23.8 electron volt. So correct choice is 23.8 electron. Next is, when a hydrogen atom emits a photon going from n equals to 5 to n equals to 1, then its recoil speed is almost, so P is equals to h over lambda according to de Broglie equation. and energy is equals to hc over. Right. It means momentum is equals to energy, or you can say energy upon c. Right. This information is given. So for two-level transition, we can write that momentum is equals to 13.6 1 over n1 square minus 1 over n2 square. Because energy is simple 13.6 upon n square, so we need to find change in energy and divide it by c. So this momentum is m into v, and that is equals to 13.6 into 1 over n1, that is 1, and 1 over 25, so you can write 24 upon 25. I don't think there is any problem in this calculation, and c is 3 into 24. Here you need to take care of a very important point, that this expression, that is 13 point energy is 13.6 over n square. It is given in electron, so we need to convert this in joule. So multiply by 1.6 into 10. Now if we want to find recoil velocity, then we need to divide by mass of an electron, that is 9.1 into 10 to the power minus. Okay, so after solving this, we'll get 13.6 into 24 into 1.6 divided by 3 into 9.1, that is already divided, so we'll get 1.6 into 25. So from here we'll get 4 meter per second. So correct answer is 4 meter per second. The next question is, a radioactive material at a given instant emits 4750 particles per minute. 5 minutes later, it emits 2700 particles per minute. So it's a half-life. So we can write the decay equation, that is R equals to R naught into e to power minus lambda. Right. Now, from here we can write e to power lambda t is equals to R naught upon R. So we can get lambda into t is equals to ln. R naught means initial decay rate 4750 upon after 5 minutes, that is 2700. Okay. So from here we can calculate lambda, that is 1 over t. T is given in minutes. No need to convert in second because we have to give the answer in minutes. So it is 5 minutes. So 1 over 5 into ln 4750 upon 2700. So if we'll calculate this, then we'll get lambda equals to 0.1129. And we already know that half-life is equals to ln2 over lambda. And ln2 is 0.693. It is divided by 0.1. So from here, 6.13 minutes. So correct answer is option C. Now let's see next question. That a free nucleus of mass 24 atomic mass unit. Emits a gamma photon which is initially at rest. The energy of the photon is 7 mega electron volt. Then the recoil energy of the nucleus in kilo electron volts. So we already know that the momentum and energy are related as momentum is equals to energy divided by C. We already know this, right? So this energy is given 7 mega electron volts. So we can write 7 MeV into speed of light 3 into 10. I don't think we need to derive this relation again. You can just correlate P equals to H over lambda and E equals to Hc. Okay, from there we so now we have expression for momentum. Now it is asking for recoil speed. Okay. So from here we can write that momentum is also related with recoil energy, that is E into 2m, where mass of nucleus is given. Okay. So P is known and we want to calculate this E. So this energy is equals to P square upon m. So P square is 7 into 10 to the power 6 electron volt whole square upon 3 into 10 to the power 8 whole square, and that is divided by twice of the mass. Okay, so this is 2 and mass is 24 AMU. So please write 24 and 1 AMU is equals to 931 mega electron. So this is 931 MeV. Because we are doing all calculations in terms of EV, so it must be written as 931 into 10 to the power 6. Okay, so just you can balance the power of 10. Okay. So from here we'll get energy that is equals to 1.1 into 10 to the 3, which is equals to 1.1 kV. So option B is correct. Next is when atomic number A of a nucleus increases. So initially neutron and proton ratio are constant. It is right that when electron proton neutron ratio is constant, then during electron capture process this number A increases. And second, initially neutron proton ratio increases, later decreases. It is not right. But if we talk about the binding energy, so at initial state when nuclear size is increasing, then binding energy increases. You can refer the graph between binding energy and the size of nucleus. And later when nucleus get heavier, then it decreases. So C is right. The binding energy per nucleon increases with neutron-proton ratio increase. It is not always true. So A and C are correct. Next is the same radioactive nucleus may emit all 3 alpha beta particles simultaneously. This is not possible. Okay, second, all 3 alpha, beta, gamma, one after another. There is no such protocol of the emission. It depends on energy and size of the nucleus that at which instant which kind of emission would take place. That only alpha and beta simultaneously, there is no simultaneous emission, so it is not right. Only one, A, alpha, beta or gamma. Please read this A as alpha. Alpha, beta and gamma at a time are taking place. It is right. Next is a 92 uranium-235 is alpha active. Then the large quantity of this element is. First, the probability of nucleus disintegrating during 1 second remains constant for all the time. It is right. Okay. Because when we talk about the probability of disintegration, then for any nucleus it remains same. Next, every nucleus must integrate by lapse of average life of operation. It is also correct. Next, quite appreciable quantity of uranium-235 will remain even after the average life. It is not correct. Because after average life, there will be a very less amount remain. Next, the energy of emitted particle is less than the disintegration energy of uranium-235 nucleus. Right. In next question, a pure large population of radioactive nucleus starts disintegrating at time t equals to 0. The number of n is the number of nucleus at present at any particular instant. T is the number of daughter nucleus at present. R is the rate of decay which daughter nucleus are produced, and then the correct representation will be. So look, if we write current number of nucleus, it is n naught into e to power n minus lambda. It means there is exponential drop. So it is correct. Now next, the daughter nucleus. So as the parent nucleus decreases, then daughter nucleus increases in same pattern. Even if we plot n and d on same graph, then the graph for n is a decreasing exponential, and for daughter it is increasing exponential. Okay. So this option is not correct. Third is about rate at which daughter nucleus are produced. So rate of daughter nucleus production is dn over dt, which can be written as lambda into n. So again, it will follow same kind of decrement. Even if you differentiate this expression with time, then we'll get a decaying exponential. So for r, this graph is right. And if we'll take ratio of r over n, so it is a constant, that is decay constant. That would not change with respect to time. So we'll get a straight line. Of graph A, C and D are correct representation. Okay, next question is a nuclear fission. In element of high atomic mass number, energy is released. Fission means combination of nucleus, so it is not right. Linear momentum, total energy are conserved, but no angular momentums are conserved. It is right, because when nucleus is combined, the orbital vector increases. Next, linear momentum, angular momentum and total energy are conserved. It is not correct. It is contradicting statement. The probability of neutrons being absorbed by fusionable nucleus increase when neutrons are slowed down. It is right, because the probability of electron capture increases. So B and D are correct. Okay, now question number 43. HB line of Balmer series of hydrogen atom is 4860. Then wavelength of HA line. Okay, so look, Balmer series For Balmer series, initial transition must take place for n equals to 2. So particles can jump from n equals to 3 or from n equals to 4. So when transition takes place from n equals to 3 to 2, it falls under category H alpha line, and when from n equals to 4 to n equals to 2, it falls under category of H beta. In this case, H beta wavelength is given, so we can just do the exercise for the wavelength of a spectral series, that 1.860 is equals to some constant, that is Rz square, into the lower orbital, that is 2 square for Balmer series, and for beta transition it must transition from n equals to 4, so this is 4 square. So from here we'll get Rz square is equals to 1 over 4 minus 16, so it is 3 upon 16, right? So it is 16 over 3 into 1, 4, 8, 60. So by using this constant, we can calculate wavelength for H alpha line, that is Rz square, that can be replaced by 16.3 into 1, 4, 8, 60 into the transition is taking place from label 3 to label 2, so it is 1 over 4 minus 1 over 9. It is 1 over 2 square minus 1 over 3 square. So we can write that 1 over lambda alpha is equals to 16 by 3 into 1 over 4860 into, that is 36 in denominator upon 5. So if we solve this, lambda dash equals to 6, 5, 6 angstrom. So option A is correct. Next is, an alpha particle of energy 5 mega electron volt is scattered through 180 degree by a fixed uranium nucleus. Means there is an uranium nucleus of 92 nucleate, 92 uranium 235. So total nucleides are 235, but 92 protons. Now an alpha particle is coming, and when it reaches to this point, there is balance between potential energy and kinetic energy. This is break point. Let's take this distance as r. After that, it will get scattered. It means at this point, the kinetic energy of alpha particle must be balanced by the potential energy of this system that included alpha particle and this uranium nucleus. So kinetic energy is given, so we can write as 5 into 10 to the power 6 electron volt. Okay. And that must be equals to the potential energy between two charges, and formula is potential energy between a pair of charge is K Q1 Q2 R. So this is K, charge of alpha particle is 2, charge of electron, and charge of uranium is, there are 92 protons, so this is 92 E, and divided by the distance. Okay. So look, if we convert this electron volt into joules, then we need to multiply by charge of an electron. So we can reject one electron from it. So R is equals to K. K is dielectric constant, that is 1 over 4 pi epsilon naught. So it is 9 into 10 to the power into 2 into 92 into charge of an electron, that is 1.6 into 10 to the power minus 19, and this is divided by 5 into 10 to the power 6. Okay. So from here we'll get 529.92 into 10 to the power minus 16 meters. Okay. Or we can write 5.29 into 10 to the power minus 12 centimeter, as we need to give answer in terms of centimeters. So this distance would be in order of 10 to the power minus 12 centimeters. Now next question is, the radius of hydrogen atom at ground state is 5.3 into 10 to the power minus 11. After collision with an electron, it is found to have radius 21.2 into 10 to the power minus 11 meters. Then the final state of the atom has the principal quantum number. So the radius is always proportional to the square of the quantum number. So we can write R1 is equals to N1 over N2 whole square. Okay. So R1 is 5.3 and this is 21.2. So from here we'll get 4, and for ground state N1 is equals to 1. So N2 square is equals to 4. It means N2 is equals to 4. So right option is option B. Okay, let's see next question. It is saying a particular hydrogen-like atom has its ground state binding energy 122.4 electron volt. So it is hydrogen-like atom, so En can be written as minus 13.6 over N square into Z square, where Z is atomic number. It is hydrogen-like. For hydrogen it is 1. Now in this case this binding energy is given 12.4. So for ground state N is equals to 1. So from here we can calculate that on Z square, that is 1.4 divided by 13.6. So it is equals to 9. So from here we'll get atomic number for that hydrogen-like atom is 3. So first option is right. Now next is, an electron of 980 electron volt can interact with an excitant. So for that we need to calculate minimum energy required to excite it. So minimum excitation would be when electron transition from n equals to 1 to n equals to 2. Right? Minimum transition from first level to ground state to first state. So delta E is equals to 13.6 into Z square, and Z is given 3, so 9 into 1 over N1 square, that is 1 over 1, minus 1 over N2 square, that is 1 over 4. Right. So from here we'll get delta E is equals to 91.8. Means minimum energy required to excite this is 91.8 electron. So this option is not correct. Next is 80 electron volt electron emerges when 80 electron volt electron interacts. Although there should be photon instead of electron, but let's consider it. So when there is 80 electron volt interacts, then no absorption would take place and it will emerges from that atom. Right? Because there is no absorption, this energy is less than required So this is correct. Now next is when 100 electron volt interaction takes place. So total energy is 100 electron. Absorption would be 91.8 and remaining portion would be 100 minus 91.8. So this would be the energy of photon which is coming out. So this is 8.2 electron. So D is also correct. So A, C and D are correct in this question. The key point is if it is hydrogen-like nucleus, then energy can be represented by this expression. Okay, next question is the stopping potential versus frequency graph of a substance is given. Here we need to calculate the work function of the substance. So look, this cutoff frequency is given, which is 5. Although there is misprint, it should be 5 into 10 to power 14. Okay. So 5 equals to work function equals to h into cutoff frequency. Here answers are given in electron volts, so we need to put this Planck constant in electron volts, that 4.135 into 10 to power minus 15 into the cutoff frequency, that is 5 into 10 to power 4. There is mistake in this. It is not written. So from here we'll get 5 is equals to 2.06 electron volt. So this option C is correct in this case. Now question number 48. 1 kilowatt transmitter works at frequency 880 kilohertz. Then the number of photon emitted per second. So first we can calculate the energy for one photon, that is h into nu. So h is 6.625 into 10 to the power minus 34 for Planck's constant, and energy is 880 into 10 to the power this is frequency. Okay. So from here we'll get energy is 5.8 into 10 to the power minus 31 for single photon. Okay. And power is given 1 kilowatt, it means 1000 watt, or we can write 1000 kilowatt per second. So total energy per second is 1000, and for one photon this is 5.83 into 10 to the power minus 30. The number of photons is total energy per second divided by for energy emitted by one photon. So from here we'll get 17.1 into 10 to the power. Here we need to adjust the power, that is 10 to the power 31 the numerator. Okay, so would get multiplied. So it is, let me check this. This is 100 into 10 to the power 30 divided 5.85. So this is 17 into 10 to the power 30. So option B is correct here. Now in this question it is saying a beam of 5 kilo electron volt alpha particle and a beam of 5 kiloelectron volts of electrons are absorbed by a target, and then two beams deliver equal amount of energy to the target per second. Their mass ratio m alpha over m is given. Now question is asking for the pressure on the target. So this is very different question. Okay. So suppose there is a surface. If a particle is striking on the surface and then it bounces back, let's assume this case. So there will be some momentum change. Okay, if we'll consider this collision as elastic, so momentum change would be equals to 2p. Okay, and there will be an impulse which leads to application of a force, that is delta p over delta t. And if we are concerned about the pressure, then pressure is force upon area. So in case terms of change in momentum, we can write delta p upon delta t into area. Right. And for this case, here this one is pressure. Let me attach P bar. So pressure by these beams on the target is equals to change in momentum upon delta t into A. And we already know that momentum is equals to root 2e into m. Okay. So if pressure is proportional to momentum, because rest of things are same. Okay, so we can say pressure is proportional to momentum. So we can say that pressure and energy is also same for both the particles. So you can say that pressure applied by these particles is also proportional to root of their mass. So pressure by alpha particles divided by pressure by electrons is equals to under root mass of alpha particle divided by mass of electrons, and this ratio is given. So it is equals to under root 7.27 into 10 to the power 3. So it would be better if we'll convert it 72.7 into 10 to the power 2. Then we'll get 8.53 into 10, which is 85.3. So right answer is 85.3 for this question. Now question number 50. That an electron of wavelength 2 angstrom and their momentum and energies are respectively. So look, wavelength is given in angstrom. Then momentum can easily be calculated by using de Broglie relation. V equals to h over lambda. Okay. So h is 6.6 into 10 to the power minus 34 divided by 2 into 10 to the power minus 10. So we'll get 3.3 into 10 to the power minus 24 moment. So in all three cases, momentums are given commonly. Now, if momentum is known, then energy can be calculated as P square upon 2A. Right. So momentum is known and mass of an electron is known. So we can place here mass of an electron, that is 9.1 into 10 to the power minus 31, and square of this 3.3 into 10 to the power minus 4. Okay, and the whole square of this. So from here we'll get the energy for the electron in this case, and that is 39 in joules. If we want to calculate in electron volts as answers are given in electron, then this energy must be divided by charge of an electron, because all these calculations are in joules. So it is into 10 to the power 90. So from here we'll get E equals to 39. And similarly, by putting mass of a photon, we can calculate the energy for photon also, or you can use Hc lambda relation for energy of photon. So option C would be correct for this question. So it's all about this chapter, this particular exercise.